Yes, so this is a common work with Simon Uppers, Sandor Gribbing, and Sayantan Sen. And as you can see, I will talk about a classical algorithm. So you might ask, why am I here? Well, it's exactly because to be able to say what kind of advantage can quantum algorithms give, we should see what classical algorithms can do. So the topic is Betti number estimation, and as I assume that several people in the audience don't really know necessarily what it means, I will start with a little introduction. So if you talk about Betti numbers, the object that we consider are called simplicial complexes. Simplicial complex is an object that is a generalization of a graph. So we have vertices, we have edges, but we can also have triangles, which are like three sets of edges, like a set of three vertices, sorry. We can also have tetrahedra that are a set of 4 vertices and so on. So it's something like a hypergraph, but it's a bit more strict because we have these restrictions. So it's also true in a graph that if we have an edge, we need to have all the 2 vertices that are contained in the edge. But we have it in general, like if we have a triangle, then we need to have all the edges around it. And for a tetrahedron, we need to have all the 4 triangles around it. So in general, if we have a k face in a graph, like a set of k plus 1 vertices, then we need to have all the k minus 1 faces around it. So for example, here in this little drawing, here we could have a triangle, but here we cannot have a triangle because one edge is missing. And so what is a Betti number? So in an intuitive way, we can say that a Betti number is the number of k-dimensional holes. So like if we look at an example, like the 0 Betti number is just the number of connected components. So if we have a torus, it's 1 connected component, so the Betti number is 1. And also in this little drawing, it's connected, so the 0 Betti number is also 1. The first Betti number is the number of independent 1-dimensional cycles. So those which are not filled by triangles, that's why they are called holes. So if it's a torus, then we see that there is the green one and there is the red one that are independent. So the first Betti number of the torus is 2. And in our little example here, this triangle is filled by a triangle, so this is not a hole. But the BCD triangle is not filled, so this is a hole. So the first Betti number is 1. And then there's a second Betti number, which is the 2-dimensional holes, meaning like cavities that are surrounded by triangles. So the torus is itself like it's a big cavity, like inside the donut. So it means that the second Betti number is 1, and the graph, I mean, we don't even have enough triangles to have any cavities, so the second Betti number is 0. And there have been some previous works on Betti number computation and estimation. A very important work is from last year by Criquinho and Kohler, who showed that it is QMA1 hard to compute exactly, but even to multiplicatively estimate the Betti numbers, and even for the special case of so-called clique complexes that I will talk a bit more about them later. So this suggests that instead of multiplicative estimation, we could look at additive approximation. So we will look at the additive approximation of the normalized Betti number, which means that the kth Betti number divided by the number of k faces in the complex. So for this, there was an algorithm by Alec, but he only considered the bounded degree case, which means that also the dimension of the complex is bounded, so it's constant. So it's a very interesting work. But for us, the second one is more important, by Lloyd, Gardner, Ona, and Zanardi, who gave a quantum algorithm that runs in polynomial time in n, 1 over gamma, where gamma is a spectral gap, and 1 over epsilon, that is the approximation parameter. So here, many people thought that there could be an exponential quantum advantage for this problem, because they give a polynomial algorithm, but at that time, classical algorithms were typically running in time exponential in k, so the dimension, like which Betti number we want to look at. And in our work that I'm presenting now, we gave an algorithm that runs in polynomial time, at least in some special cases, like if we also have, for example, constant gamma and constant epsilon, or in the special case of clique complexes, and especially for large k, which is very important because, as I said before, So previous classical algorithms were exponential in k. So it especially people thought that for large k, we could have a big quantum advantage. But our algorithm, at least in the case of clique complexes, is exactly more efficient when k is large. So now let me go into a bit more specific details about what we are looking at. So a bit more formal definition of simplicial complexes after the introduction. So in a simplicial complex, we have a set of vertices, a set of edges, which are called one faces. So they are two vertices, a set of two faces that are three vertices, and so on. And there is this restriction that if we have a k face S, then all of its subsets basically have to be also in the complex. And the clique complex is a special case. So we are given a graph G, and we say that the complex is just going to be all the cliques of the graph. So the k set, the set of k sets is going to be the set of k plus 1 cliques of G. So for example, if we have this very little graph here, then the complex is going to look like this. And by this, I mean that we are going to have three vertices, three edges, and there is going to be also a triangle in the complex. An important object or operator that we have to look at when we look at the simplicial complexes is called boundary operator. As we can see in the example, it does exactly what we would suggest from the name. It assigns to a complex its boundary. So for example, here we had a triangle, and then we will have the edges that are the boundary of the triangle. So in a bit more detail, for each face, for each k face, that is k plus 1 vertices, we will assign a basis vector. That's why we have these cat signs here. And we are going to look at oriented faces, which usually just means that we orient the faces like in an increasing order, for example, from A to B to C. That's this little arrow here. And then the boundary operator is going to assign to a k face k minus 1 faces. So the boundary of this A is just going to be the signed sum of the edges that we get by omitting one vertex. So we have A, B, C. First we omit A, we get BC. Then we omit B, then we get AC, but with a minus sign. And then we omit C, so we get AB. Minus AC is the same as CA, so we get exactly this triangle. So now we can define more formally the Betti numbers. So as I said before, in an intuitive way, it's the number of k-dimensional holes in the complex. So yeah, the definition is, it looks like this. So the kernel of the boundary operator minus the image of the other boundary operator, and we take the dimension of all this. But what does it mean? Like, what can we say about it in an intuitive way? So first we can observe that the boundary of a boundary is always 0. For example, we had this little example just on the slide before. And if we apply again the boundary operator on this example, then we will see that everything will cancel out and exactly will get 0. And this is also true in general. So we can ask the question, what other vectors are mapped to 0? So what are those vectors that are mapped to 0, but they themselves are not the boundary of another object? And this is exactly the kth homology group. So those which are in the kernel of the kth boundary operator, so they are mapped to 0, but they are not in the image of the k plus 1 boundary operator, meaning that they are not the boundary of something else. So these are exactly what we are interested in. These are something like a hole in the complex. Another useful and important object or operator for us is the combinatorial Laplacian that we can define this way. So we have this down operator and the up operator. The down operator is defined by the k boundary operator and the up operator by the k plus 1. And so we can see, if we look at it a little bit, that the kernel of the combinatorial Laplacian is exactly the homology group. By that, we get an equivalent definition for the Betti number, which is just the dimension of the kernel of the kth combinatorial Laplacian. So what does this combinatorial Laplacian do? Why is it called Laplacian? Well, we can look at it as like a generalization of graph Laplacians, because this down operator, what it does is something like it takes a step down from k faces to k minus 1 faces, and then takes a step back up, because first we take the boundary. So from k faces, we go to k minus 1 faces, the k minus 1 faces that are contained in our k face, and then we go back up with this adjoint operator to k faces. And the up operator is the same, just it steps one up. And so if we look at the example when k is 0, then we exactly get back the graph Laplacian, because then we cannot go down. So the down operator is just 0, because there are no minus one-dimensional faces. So we can only go up, which means that we start from a vertex, and through an edge we go to another vertex, which exactly means that we're going to have non-zeros in our operator where two vertices are adjacent. Okay. So now, after this long introduction and preliminaries, let's look at our actual algorithm. So the main ideas of our algorithm are going to be summarized here. The first idea is, if we take this matrix H, which is defined using the combinatorial Laplacian and the maximum eigenvalue of the combinatorial Laplacian, then we can see that the rth power, so the trace of the rth power of this matrix, is going to be close to the kth Betti number if we take a large enough R. We will look at it in a bit more detail later. And the second idea is that we can estimate this number, this trace, or its normalized version, by a path integral Monte Carlo method. But what does this mean? It means that we will just take R steps on a Markov chain of k faces that is defined by H. Because if you write just the definition of this trace, you will see that here we have R, like a product of R H's. And if we just put some identities between, then we see that what we get is we start from a k face I0, and then by H we go to another k face I1, then by H we go to another k face, etc. So we take R steps on a Markov chain of k faces defined by this matrix H. So now it's clear what our algorithm is. We pick an initial k face I0 uniformly at random, and then we take R steps on the Markov chain defined by H. So these are the transition probabilities. And this is efficient to calculate because of some properties of the combinatorial Laplacian, because we know that there are at most order n square possible neighbors. So it's efficient to calculate these probabilities. And so this way we will get an estimate of the normalized trace of the rth power of H, which we know that is close to the Betti number. And if we repeat it enough times, then by standard concentrations bound, for example, one called Höfding's inequality, we get a delta additive estimate of this value, which is close to the Betti number, the normalized Betti number. And we can further improve it a bit by using Chebyshev polynomials. So instead of the R power of H, we can write it in a Chebyshev basis, and so this way it will be enough to estimate powers of H up to power around square root of R. So now a bit about the analysis. So why did we take this matrix H? Why does it work? So we saw before that the alternative definition of the kth Betti number was a dimension of the kernel of the kth combinatorial Laplacian, which is just the number of zero eigenvalues of the same matrix. And here we have an assumption on the spectral gap of the combinatorial Laplacian. So it has to be bounded, lower bounded by gamma times the maximum eigenvalue. And this way, if we take this matrix H that we were looking at before, then we are going to get a matrix where instead of the zero eigenvalues of delta k, we are going to have one eigenvalues, and the gap is going to be gamma. And this way, now it's easy to prove that the trace of the rth power of H is between beta k and beta k plus epsilon. So if you look at the normalized Betti number, so if we divide everything by the number of k faces, then we exactly get that it's an epsilon approximation of the Betti number. And yeah, the other thing that I already mentioned is that this trace is exactly these are steps on the Markov chain. And this can be interpreted as like just an expected value. So that's why we can just take several walks of our steps on this Markov chain, and then we get a good approximation of this trace. So in the special case of clique complexes, we can go further because there is an additional property of the combinatorial Plascian in this case, meaning that it's even sparser. So instead of order nk possible neighbors, we only have less than n possible neighbors, so less than n non-zeros per row. And then this means that the first, so the one norm of our matrix H is going to be lower than in the general case, which means that it is enough to take less samples when we apply Hoeffding's inequality. So the complexity of our algorithm is going to be better. So what are these complexities? So in general, we can get an epsilon additive approximation of the normalized Betti number in this time. So here the square root is exactly there because of the Chebyshev polynomial trick. And for clique complexes, it becomes n over lambda max here, which means that in the clique complex case, if k is omega n, then we know that the maximum eigenvalue of the combinatorial Laplacian is going to be the order of n. So this way, this is going to be a constant. And it means that if, for example, gamma is omega 1, so it's a constant, and epsilon is 1 over poly n, then this whole thing is just going to be a polynomial. Or if epsilon is the thing that is constant, then gamma can be 1 over log square n, and then we still get polynomial running time. But even in the general case, if both of them are constant, then we get a polynomial running time. So what does it suggest? Well, we find that for example, for clique complexes, which is a very important special case, there is just a little place now where there can be an exponential quantum advantage, because the quantum algorithm was running in time polynomial in n and 1 over epsilon and 1 over gamma. For us, it cannot be 1 over poly n at the same time, epsilon and gamma. So there might still be a little areas, a little region where there is an exponential quantum advantage, but it's not true in general. And so, yeah. So some open problems. So what can still be done is make it better, which I just mentioned. Like, can it be the case that also it can be solved with classical algorithms in polynomial time in n, 1 over gamma, and 1 over epsilon? It is an open problem. Or can we give a lower bound? So can we say that it cannot be the case? Or with the same method, can we estimate some other properties of delta k? And a thing that I forgot to make a slide of is what is it used for? Like, why are Betti numbers and simple shell complex is useful? Well, there is a field called topological data analysis, which does exactly this, that we have a bunch of data points. And for that, we can assign a simple shell complex based on the distances between these data points. And then now it's a very current thing to look at the topological features of this data set because they are somehow robust. And for example, if we look at the 3D image analysis, then it is very important to look at the topological features of the data that we're looking at and so on. So yeah, that is the motivation behind the whole algorithm. So with that, thank you for your attention.
Thank you for the nice talk. Are there any questions?
Thank you. I have a question about the lambda max.
Yes.
So it seems it's important that you know it beforehand, because if it's too low, you might get negative eigenvalues and maybe a sign problem. But if it's too large, then the complexity of the algorithm suffers. So could you comment on how to get the lambda max?
Yeah, so it's a good question. So we just say that we assume that we are given this gamma. Like the algorithm is given this gamma, and with that we are basically given like, yeah, so it is something like, yeah, so we suppose that something like an estimation of lambda max is given to us.
And is this something that you could estimate from the problem efficiently, or?
No, but it's the case for all the other algorithms also. Like they assume that there is this gap, and they just use it.
Thanks for the talk. Maybe I missed this, but you spoke at the beginning about the QMA1 hard result of topological data analysis. Can you just like elucidate why the setting here is of like classically tractable?
So the QMA1 hardness, it's for the exact computation and also for the multiplicative estimation of the Betti number, but here we are looking at the additive approximation. So if you wanted to look at, if you wanted to calculate a number that is between beta k times 1 plus minus epsilon, that would be hard. But here we are just calculating a number which is between beta k plus minus epsilon.
Little follow-up is that useful in topological data analysis?
Well, I don't work in topological data analysis. I think so. It can be, yeah, depending on, I guess, the application.
Thank you.
Thank you. So maybe a follow-up to that question. First of all, by the way, great talk. I really appreciated it. I learned a huge amount just by the first half of the talk, really being very clear about things. But I wanted to understand, because this is normalized Betti number, is additive good enough?
It's a good question, again. Well, this is what we can do.
Let me ask it differently. What do we know about the norm EK that shows up in that denominator?
Yeah, so in general, it can be exponential in K. But for example, if we look at 3D image analysis, then we are only in 3 dimensions. So then I guess it's not that bad. But yeah, if we have very high dimensional data and high dimensional complex, then it can be very high. So yeah, it can get... yeah, so it's true that it's a problem that if the dimension gets very high, so if K is big, then even the spectral gap assumption is basically just, like, it's not too realistic, let's say. So yeah, it's true that for very high dimensions, it can be problematic in practice.
Thank you.
Hi, thank you for your talk. It was great. I want to ask about the key routine that you've used. And what I'm curious about is, when we think about the algorithm that you talked about, the quantum algorithm, the LGZ algorithm for topological data analysis, it's effectively doing trace estimation. And then if you come up with an algorithm that's doing the same problem, and it looks like you also have a trace estimation algorithm. So my question is, have you considered how this might be usable beyond the problem of TDA, but maybe like of Betti numbers, but to like other things? Because trace estimation is a pretty generic thing.
Yeah, so that's exactly one of the open problems that I mentioned at the end. Like, can we estimate other properties of delta K? Can it be used for some other, so can a similar method be used? It's a good question. We haven't thought about it yet.
Yeah, and I also have a small question about the parameters. I wonder if you could like say when you think it might be the case that a quantum algorithm could still achieve an advantage. So you talked about how your algorithm can't be like polynomial in both epsilon and gamma, but the quantum algorithm can. So what are those settings where you are polynomial in both epsilon and gamma? Or need to be because they're big, I mean.
I would say that if you want to have a good estimation, meaning that it's 1 over poly n, and at the same time you are given a complex that has a combinatorial Laplacian, that has a spectral gap that is 1 over poly n again, then in that case it, yeah. So depending on the complex and on the precision parameter, you.
So it's kind of like the setting of a good estimation of a sort of well-conditioned, well-behaved TDA problem. That's the setting where the quantum algorithm is doing well?
Yes, so, wait a minute. Yeah, so this gamma is, right, it's lambda 2 divided by lambda max. So it means that if lambda 2 is, so if gamma is 1 over poly n, it means that there is, so it means that lambda 2 is very close to 0, right? So the spectral gap is small. So if the spectral gap is small, then yeah, then the problem is harder, let's say. So that's where quantum algorithms can still be better.
Thank you.
Okay, are there any other questions? If not, let's go to lunch.